Discovery's 4 computers now have primary control of critical vehicle functions.
All right, everyone, welcome to today's ASRG webinar. But before we get started, I'd like to tell you a little bit about ASRG and get some of the legal stuff out of the way. ASRG is a nonprofit organization founded to support the development of the automotive security industry. We have developed a platform and a community to share knowledge, communicate through networks, and to build value with collaboration. This is a community for you, built by you, with the goal to protect our friends and family when using automotive products. If you want to learn more about ASRG or get more involved, please visit our website at www.asrg.io or send us an email at hello@asrg.io. Before we jump into the presentation today, let's get some of the legal stuff taken care of. The views and opinions expressed in this webinar are the views of those that have made them. They do not represent views or opinions of ASRG and are to be considered as informational. The use of this information is to be used by the individual and/or organization at their own risk.
Hello everyone and welcome. As we move into today's session, we are addressing a massive shift in automotive world. We have moved past the era of cars with apps and entered the era of software-defined vehicle. With over 100 million lines of code in a single vehicle, the attack surface has grown exponentially. Today, we are looking at how to protect that code, specifically focusing on memory-based vulnerabilities that criminals are actively targeting. To lead this discussion, we are joined by someone who operates at the very highest level of cybersecurity and national defense, Joseph Saunders. Joe is the founder and the CEO of RunSafe Security. He leads a team of former national security experts on a mission to secure the world's most critical infrastructure, from US Army and Navy to the global giant like Lockheed Martin and GE Vernova. But Joe's expertise does not stop at the software. He's also the chairman of Ask a Sage, an AI platform transforming how government and the business operate, and the founder of International Resilience Institute, where he works to quantify the power and cohesion among nation states. With that, I would like to welcome Joe to the stage, and just a note to the audience, we will be taking a Q&A at the end, but feel free to drop your questions in the Q&A section. On the right side, you will be seeing it, or in the chat. We will be taking it at the end once Joe's presentation is completely done. With that, I would like to give the virtual stage to Joe. Joe, stage is yours. Please go ahead.
Thank you, Jitendra. And I'd like to just begin with the importance of this dramatic shift and continued shift that Jitendra had talked about in terms of the value within the automotive industry software-defined vehicles are bringing, and whether that's through entertainment and onboard experience within the vehicles, or the autonomous driving and related software that helps enable all that. What we're seeing is a continued value creation around software-defined vehicles within the industry, and by 2030, over $650 billion of the industry will be related to this aspect. And even further, what I have seen with all the automotive OEMs that we work with, there is a dramatic shift of team members who have software backgrounds in these companies, and a number of these OEMs are becoming software companies as much as automotive manufacturing companies. We have seen this in a couple different ways. We have seen joint ventures with key software development organizations. We have seen the auto industry hire leading software employees from places like Apple and Google. Even RunSafe has a partnership with a company called Critical Software that writes a lot of the infotainment software and other mission critical software on devices for the automotive industry to enable enhanced features. And so just that alone demonstrates that the predictions of this shift in value creation within the software-defined vehicles is significant. And by 2030, it will represent over 20% of the market for sure. So with that, this dramatic shift in focus on software over the past several years and the continued focus given autonomous driving, what we've seen is the two key items that are driving that. And one is the value proposition to the passengers, to the consumers, so that they have the most complete experience possible. And so the OEMs can create relationships through value-add services with their customers and not strictly be like the old days, a place where you buy a car and occasionally have it serviced. And so the value proposition to consumers through personalization and connectivity is a key aspect of this. But so is, of course, autonomous driving and electric vehicles and the ability to manage software updates over the air. And all of these items, all four of these items, the consumer benefits, the autonomous driving, the electric vehicle, aspects of it, and the over-the-air updates all present, an increase in software that's used on these vehicles. And so with that, we do see that there are over 100 million lines of code on vehicles today. And that's a significant number for a couple different reasons. One, it's a significant number because it's a lot of software to maintain, a lot of open source software to be concerned about, especially with end-of-life designations of software components, since cars last so long these days. But two, it increases the attack surface given greater and greater software modules are on these vehicles. And so with over 100 plus applications, you can imagine all the different options an attacker might have to find their way on the vehicle. And we see that happening due to radio frequency, due to Bluetooth, due to internet connectivity, and all sorts of ways that not only vulnerabilities are introduced, but either malware or remote attacks can occur. And so with the greater surface area of software, there's a greater surface area, attack surface. And when we think about that consumer experience and we think about these value-add services of autonomous driving and related autonomous features, we need to keep in mind then, with the increased attack surface, the importance of safety in vehicles. And cybersecurity is just one way that safety can be compromised. And so with the increased software surface, we need to be even more mindful of the safety considerations and the cybersecurity aspects that help ensure that great experience for consumers. And so when we look back then on the related attacks across the landscape, we found four key stats that I think are helpful to understand the significance and the severity of what cyber incidents could result from. And the first thing of note is that over 92%, or let's say 92% of attacks in 2024 and continued in 2025 were remotely executed. And that is because of the connectivity, and it's because attackers know how to gain access remotely. And so that's a significant statistic, because if you went back 15, 20 years ago, that number would be negligible. And it wasn't until about 2014, 2015, when we saw the first major headline related to a remote attack. And now with that, and that was the Jeep controlled attack with white hat hackers. But today, any of the executed attacks on vehicles, 92% of them are remotely executed, and it's a significant number. We also know that 35% of those attacks involved system manipulation, meaning ways to impact the driving of the vehicle or manipulate the vehicle itself. And so that also is significant. Yes, some of it could be kept within, say, the infotainment systems, but even 35% is a significant number to say it involves system manipulation. And along those lines, then, what we have seen is 60% of those, incidents affect millions of cars. And we'll walk through a couple of examples. When you think about, the software components across vehicles, that is one of the common factors from vehicle to vehicle is there is similar software or exact same software from vehicle to vehicle, or at least the underlying, say, operating system or the libraries and the open source packages that are used are, shared and used across OEMs and across platforms. And so that, in effect, creates the point, the obvious point of failure is that there's common software across the vehicles. And with that, we saw three significant attacks. We saw an increase of 3x of the number of massive attacks from year over year. And so with that, this report, of course, came from the Automotive and Smart Mobility Cybersecurity report from last year. And it's been one that we've used in our conversations with our OEM partners. And so in addition to that, we have seen the perspective from consumers increase in terms of their level of concern. And a lot of them believe that remote hacking is possible. They've certainly seen some of the headlines. And so they're aware of cyber attacks in other industries. And so it transfers to the automotive industry and the software-defined vehicles. And consumers do believe that protecting physical safety is certainly more important than the personal data. But of course, privacy is significant from a regulatory perspective as well in the EU, in the US, and across the world. The privacy is very important also. And with that, I think the findings from a survey from last year suggest that consumers and passengers are expecting OEMs to do something about it, and it could influence their decisions. So we have an increase in attack surface, we have common software, we have consumers have expectations, and we have a motivation from automakers to continue to differentiate, especially in light of competition from China, for OEMs to have cars that meet the needs and the desires and the requirements of their passengers or their customers. And so with that, the increased attack surface does have common software, but also then that software has common types of vulnerabilities, which is what gives me hope that we can maintain the same level of safety as we've experienced in the automotive industry for a long time. And with that, though, there are some areas of particular vulnerability in software-defined vehicles that we need to be mindful of and think about from a cybersecurity perspective. So, of course, infotainment systems is a key area because it can be a gateway to access other components on a vehicle. There is, of course, data in location information in there that affects that privacy and that concern from consumers. And it can lead to lateral movement to other areas on vehicles. And so infotainment systems with their connectivity, with the value-add services, with the tiebacks to the manufacturer, with the internet services that are enabled on these vehicles, that's a common access point. And then once you have access, where the safety concerns come in are with remote execution and ways to start to compromise either the driving assistances, the advanced driver assistance systems, the ADAS systems, or the electronic control units, the ECUs. And with that, on the ECU side, what we see is there are real-time operating systems that are common across vehicles. In fact, one manufacturer's real-time operating system, which is really a performance operating system geared towards reliability and predictability and determinism to ensure that safety functions and functions of these ECUs operate. Since there are manufacturers whose real-time operating system is deployed across over 250 million cars around the world, you can imagine that if there are vulnerabilities in the RTOS underlying operating system, it leads to a dramatic level of exposure and in fact can lead to remote code execution on embedded systems in general. And then of course, with the advancements of ADAS and within the security compliance realm, there are 4 levels of compliance within the ASIL guidelines, from ones that, the most strict levels are ones where there's full autonomy, but we have a lot of driver assisted capabilities on vehicles that also require a significant level of safety, even though they're not fully autonomous. And so it's in those areas we have seen memory safety vulnerabilities related to CNC++, as we've seen in ECUs as well, as we've seen in Linux systems on infotainment systems. But in particular in this area, when an attacker can gain access to buffer overflows, that can potentially jeopardize the safety critical code and enable attacker to perhaps do something that the system wasn't originally intended. And so there can be onboard compromise and compromise of the real-time systems in there that could create concern for people. And the concern then for all of this, I still roll all that back up to safety for the passengers. And so these are common types of vulnerabilities, and these are main areas, components on vehicles where those vulnerabilities could get exposed and exploited. And along those lines, in 2025, infotainment systems, again, no surprise with infotainment systems that that is an entry point because of all the connectivity there, and then the potential to move across vehicles in some situations. And so we saw remote access in Subaru Starlinks back in January last year. We also saw unauthorized access in the Nissan Leaf platform or vehicles in April. And then there's the perfect Bluetooth stack set of vulnerabilities from last year in July that led to one of those massive exposures across many vehicles. And it was on 350 million vehicles had that software. So if we go a step further and really diagnose an example of what can happen when there is a vulnerability like this, a good one to talk about because it was transparently shared, it was addressed by the OEM, in this case Tesla, who does a very good job of sharing vulnerabilities, and they have good connectivity to vehicles to do software updates. And with that though, there was one of these devastating types of vulnerabilities with this CVE from 2022, and it's a classic buffer overflow. And for those that don't know what a buffer overflow is, it's really a way to get system level information as an attacker to then take remote code execution and control of a system. And what you're doing is getting an information leak about how the inner workings of the software operate so that an attacker can leverage their exploits or their ability to manipulate software. Once they have access to the memory inside these systems, they can start to do things that the car wasn't intended to do originally. And so it allows local attackers not only to escalate, but potentially take arbitrary code and do what they want with it, because they're replacing code in memory with other functions, or they're reordering code to do nefarious things that were never intended in the first place. And so these types of buffer overflow sets of vulnerabilities can lead to remote code execution, arbitrary code on a target system. And in this particular case, it was a Broadcom driver, the BCM HD driver. And so obviously Tesla was able to disclose this and had worked with its software supplier. But what it shows is the complexity. It starts to show the complexity and the dependency that OEMs have on their software supply chain. And so in this case, Broadcom provided a key driver in this equation. We know a lot of the software on these infotainment systems rely on open source software. There's common RTOS systems across platforms. And so the software supply chain becomes a major area of responsibility for OEMs to think through what their security requirements are, because you can see a vulnerability from one supplier can lead to a number of vehicles being exposed to cyber attack. And so then another example, also looking at the Bluetooth chipset, was to break into Tesla's infotainment system, and from there, in a similar way, gain root access. And so we featured this on our podcast called "Exploited: The Cyber Truth," where the security researcher from this particular exploit was discussed. And in this case, in a pwn-to-own contest, going back a couple of years, there was the ability to then compromise that system very, very quickly. So I highlight the fact that if you can compromise using heap overflow vulnerabilities and the ability, again, to manipulate based on errors within the way software functions load into memory, you can do a lot of damage and gain root access. And from there, you have really control of many other subsystems. And so, with that, I think, kind of tying this with the previous slide, again, the software supply chain is very key. And one of the key things about that is security researchers that are helping OEMs are very, very good. But when there's motivated nation states and motivated hacker groups, they're also very, very good at finding exploits or finding vulnerabilities and producing exploits. And with the advent of AI, we know that AI can help produce today exploits faster than we can patch. And so for autonomous driving, it's a particular area of concern. And for connected vehicles and software-defined vehicles, it's a particular area of concern with the advent of AI helping attackers to develop exploits. And so generally my view on that is, yes, it's a concern, and we need asymmetric ways to shift the cyber defense to ensure that AI is not a runaway train, so to speak, in this case. But there's other areas and ways to help fortify all these vehicles. And I'm a firm believer in the standards that are developed to help keep our software-defined vehicles and all vehicles safe for passengers and safe for drivers. Certainly the ISO 26262 with ASIL levels for software integrity, is a key area. Also, standardized architectures built around AutoZAR is sort of an industry adopted standard by many OEMs, and there's other standards that are coming in the autonomous software arena that will leverage pre-approved kind of open source platforms for autonomous driving. And so as those common platforms get adopted, like AutoZAR and future autonomous platforms, as well as EU regulations around cybersecurity management, it becomes very vital. And so much so from a national security perspective, over the past couple of years, the U.S. Commerce Department has developed, through its Bureau of Industry and Security, a concern about connected vehicles and has developed a requirement for all covered vehicles that include software-defined vehicles. By 2027, should an OEM want to sell their cars in the United States, they need to attest that there's no software written by entities in Russia or China. And so the way to do that is to generate a software bill of materials and develop that country of origin requirement to help you ensure that you can do that attest by 2027. And it's something that we take very seriously at RunSafe, something we've been involved in and are very concerned about helping ensure that we make that a very easy automated process for OEMs to develop the artifacts and the data and the understanding of the risk in their software supply chain and their SBOMs, so that they can do these attestations easily and quickly and efficiently. So with that, I do have a handful of ideas around strategies for protecting software. I had mentioned the importance of the software supply chain and the view, I think, across the industry with the motivation to comply with the Bureau of Industry and Security within the U.S. OEMs do have practices and regulations encourage these practices to look deep into the software supply chain, and even 3 levels deep is what is expected. So tier 1, tier 2, tier 3 auto suppliers are the responsibility of the OEM when it comes to the country of origin. And so identifying vulnerabilities, identifying open source license checks, identifying country of origin, and incorporating that data into automated ways to build and produce not only a complete and correct SBOM, but a compliant one that enables you to boost your security posture around these risk areas. So addressing the software supply chain is a major area, of course, in the world of software-defined vehicles, and will only become more and more important as OEMs become even more significant software development organizations in general. And then certainly the RTOS coordination, there is a real concern when you look at software that's across so many vehicles. Could that become a key area for attackers to compromise? And if you can gain access to the OS, what can you do at the user level with the applications? And so, a way to protect software then is to ensure that you provide, which I'll talk about in more detail in a second, cyber defense, not just for the operating system, but do it in a way where there's still deterministic behavior for the vehicle itself so it can comply with safety standards. You don't do it in a way where there's no overhead impact, and ensure that it complies with the safety critical standards requirement. And that is through the use of runtime memory protection in the top right. And so it's very easy to deploy ways to ensure that those things that we featured earlier, like heap overflows, buffer overflows, those out-of-bound read writes, and related memory corruption errors that are so predominant in this kind of compiled code across these vehicles, the ones that enable real-time operating systems and their applications to operate that kind of software, also happens to have a lot of memory-based attacks. It's an area of target for, as we showed earlier, for attackers. And so ensuring that memory exploits cannot happen, and it's coordinated with the RTOS system and is complementary to the vulnerabilities that you find in the supply chain, gives you great level of security and certainly safety for passengers going forward. And with that, as further framework integrations are done, we mentioned AutoZAR and their standards around POSIX integration, so we can communicate with different components within software, and certainly the ASIL requirements within ISO 26262 are very helpful. And the future standards around autonomous driving and software frameworks there means that it actually helps everybody when there are common frameworks like this. And I know I talked about the risk of exposure even with real-time operating systems, but the benefit of having common software frameworks and software is we have more visibility into what the underlying vulnerabilities are, and we can identify them in ways that ensure safety and compliance or safety and security compliance are maintained. So on the one hand, maybe it could lead to greater risk exposure. On the other hand, these common frameworks lead to greater hardened software aspects and really resilient software development practices. And so these are strategies for protecting the software. And of course, all that needs to be done by balancing safety and security while the OEMs continue to innovate and meet the market demands, both from a competitive landscape with challenges from manufacturers across the world, but also to ensure that the requirements meet the personalization and the consumer expectations of value add. And so there's no doubt that the software-defined vehicle is here to stay. It's a key area for differentiation across vehicles going forward. Those that buy the best or provide the best services, the best experiences, the best features in vehicles are going to be some of the best automakers going forward in the highest demand vehicles. And then those that are enabling electric vehicle capability, autonomous driving, and other personalization experiences are key. But the key is we, of course, want to embrace the push towards software-defined vehicles and that innovation, but we need to do it with safety in mind, and safety begins in part with software security in the world of software-defined vehicles. So those are my prepared remarks, and I'd be happy to follow up with questions, but certainly there's some key takeaways. Address the memory vulnerabilities, security equals safety, and innovation and security are essential in the competitive landscape in the automotive industry. And certainly we want to embrace all of this and enable safety and security so passengers are getting the proper experience and meeting their expectations. So with that, I'd be happy, Jitendra, to turn it over to questions and see where we are from that perspective.
Thank you, Joe. It was really wonderful. And we have a couple of questions. We will take it. So the first question, you can see it, the presentation, the question.
Yeah.
Joe?
Yeah. So
I'll say, hi, Joseph. So since we are seeing SDV is not primarily implemented, but will be soon coming, are there any audit and testing guidelines for it?
yes, there are emerging guidelines for software development practices and for testing guidelines, and certainly, there are. If you look at the POSIX requirements and then you look at the ASIL requirements, there are a number of things that need to be followed, including the ASIL requirements, especially when it gets into the autonomous driving. And so what that means is that, generally it includes, doing security scanning and testing and identifying vulnerabilities and finding ways to mitigate those vulnerabilities so they can't be exploited. So, I'd be happy to follow up further if you want exact links to guidelines. But with that, I think if you look at the requirements in 26262 and ASIL, as well as, the POSIX compliance requirements, you'll be well on your way to get there.
Thank you, Joe. I'll move to the next question. So coming from Web VAPT, so it's a vulnerability assessment and penetration testing sector. Can I say it would be like a black box testing we need to do for a vehicle with these connected features?
Yeah. So this is a good example of where the web-based sector intersects with the vehicles, and where there has been traditionally been these hardware components that do have rigorous safety testing requirements. And if you look at the autonomous driving safety compliance requirements, you'll see that you actually have to go pretty deep into reviewing the code itself and documenting the code and ensuring that the code always behaves the way in a deterministic way. And so I would say that it goes even beyond what you would consider black box testing for these vehicles. There are regimented ways to ensure, and in fact, when you do the safety compliance on vehicles, not only do you have to do your self-assessment and go through all the safety testing, and do the testing and do the scanning and do the mitigation and document the lines of code and look at the determinism, but you have to turn that over to a third party who will then validate the same findings in order to be safety certified. And so that's a significant undertaking. Now, the good news is there are ways, once an OEM certifies a platform, they can maintain updates to that platform in a way to make that ongoing compliance efficient. But it raises a couple points about testing that I want to highlight. And so just because you test and you pass when you release, it doesn't mean you don't have future exposure to vulnerabilities. And of course, what we've seen in these safety critical systems, where they are written in native code, compiled code, written in C and C++ languages, that these memory-based vulnerabilities are often not found in the original initial testing. And so what I would encourage everyone to think about then is, for two reasons. One, what if a new vulnerability emerges? Do you already have protection in place so that you stay in compliance? And then two, as open source components reach end of life, does the OEM and do their suppliers have a plan to ensure that safety and security will be maintained even if a software component reaches end of life? And what I've seen in the EU with certain manufacturers and OEMs in Europe, what I've seen is that they are starting to expect suppliers to maintain software for up to 25 years. And that's presenting a series of potential questions about vulnerabilities and security that relate to it. So I think it's best to look at the standards and not assume that scanning and testing will be sufficient. You need to think about the broader complex of safety and how you'll ensure compliance for 25 years, not just for that particular release.
Thank you, Joe. It was really a good explanation and the connectivity between different topics and giving a broader perspective. Why not to consider only one, but think from the broader way to ensure that we are compliant. I have one more question from Joe. Would you mind sharing your email again, please, as I didn't manage to catch it at the start. So I think after this slide, Joe, you will be sharing the contact details, right? Okay, I'll take to the next question.
Yep, here, I'll just put that on there. Thank you for prompting me there. Yeah, happy to work with everybody.
Another question we have. Hello, Joseph. If runtime memory violations are already caught during SPA checking across MISRA guidelines, could there still be missed violations?
Absolutely, and that's one of the areas of concern. And so what we have seen, and I know you list software composition analysis here, what we've seen from scanning tools and then software composition is they catch, often they'll catch known vulnerabilities, but there is a significant number of underlying weaknesses in memory that enable return-oriented programming gadgets and chains to be exploited by developers. And so you do need to go further than just patching the known vulnerabilities. And that is part of the mission of RunSafe, is to lock that all down at the memory level. And what we've seen, and I don't have exact numbers from all SCA tools, some folks do fuzzy tests or fuzzing. Other people are, doing other forms of pen testing. They're certainly doing software composition analysis. They're certainly doing scanning for vulnerabilities. But I'll just highlight that even in the Linux operating system, as an example, scanning tools only catch about 5 or 10% of the potential weaknesses in memory-based weaknesses. And so that's a study that was put out by North Carolina State University. And the issue is that many of the 0 days that emerge later are built on memory vulnerabilities that weren't identified in normal software composition analysis or pen testing or fuzzing or other tests. And so from the run-safe perspective, this is where we think that these weaknesses, if not addressed, can lead to a non-deterministic response in an operating system or in an application on a vehicle. And so you absolutely have to secure the memory in order to ensure long-term that you're going to stay in compliance, but more importantly, maintain passenger safety.
Thank you, Joe. I'll take my question. So when we are talking about like memory prediction, definitely the latency and the time trade-off is the one of the topic which comes most frequently than we can think about or talk about. So how like more protection we put it at the memory, does it impact the latency or how it handles it?
Yes. And the key is that some organizations will enable settings within their compiler to allow for things like address space layout randomization. And the problem with that is easily defeated at the by attackers because it's simply an offset. So going back to one of the examples today, with a single information leak, you can recreate the makeup of the entire memory map and then still administer as an attacker your exploit and deliver a payload as desired and access system calls to do things to manipulate even the operating system as an example. And so traditional methods were not even working. But the challenge then is how do you solve for that and introduce low overhead or no latency, as you say, at runtime from a system overhead perspective. And the way we've approached it at RunSafe is to ensure that our security protections are applied pre-execution at system startup without introducing any new software into the system and at runtime. And so there's no new software and there's zero overhead. And you probably say, well, you didn't quite answer the question. So what I'll say is we relocate where functions load into memory before execution begins at runtime. And so it's pre-execution, we relocate the functions in memory, and we do it in a way that even with a single information leak, the attacker can't find where all the functions are in memory. And so it's a memory-based relocation that complies with determinism from a safety perspective, but comes with zero overhead. And so when ECUs have constrained memory or power, or when there's general purpose operating systems or embedded systems, embedded Linux on devices or build root or Yocto-based platforms and infotainment systems or real-time operating systems, doing this ensures that you stay in compliance with safety requirements and you introduce no overhead. So I hope that answers the question, but the quick answer is we do it pre-execution.
That's an interesting one. Okay, so I think audience can have a contact of Joe to reach out for any further questions and queries. I think like this presentation sets more of a curiosity, at least for me, and I'm seeing it from the audience perspective as well. So definitely you will have your inbox filled with a lot of queries and references to be asked for this one. So I will leave it to that. And Joe, I would like to thank you for your all insights. And it's clear that the line between vehicle and computer disappears. Our approach to the safety must be as dynamic as the software itself. So it's great to have you today here. With that, I would like to thank you, our audience, for your time. We hope you leave today with a clear roadmap for integrating the memory safety into your own automotive projects. And Joe has set and given a lot of insights and the references, which definitely gives a lot of brings a lot of curiosity to think from your project perspective and try to build those, because proactive approach is one of the most effective approach you can have it to secure your products and the vehicles. And when it comes to the safety, that becomes a little more complicated and serious thought to give to. We look forward to see you all in our next webinar. With that, I would like to say goodbye to all, but not completely. We will see you the next time. And Joe, thank you so much. We really had a great pleasure listening to you and with all the insights, and we hope to have you in the future as well. With that,
Thank you,
thank you
Jitendra.
all. Have a good time. Bye-bye.